Hi, welcome to part 2 of recap of root array, root locus, Bode plots and polar plots. These are the things we should be knowing. Yeah, with this, so now we know there are so many points. There is a procedural way of writing the root locus. Now the question is it necessary to do all the procedures for all the given transfer function? It is not so. Let us start with is it necessary to find break away point to plot root locus. Now the question is it necessary to find the breakaway point to plot the root locus? So let us try to understand what is this breakup point and is it always required to find. And before that, we'll just take a question before this. So what is this dk by ds equal to 0 to find the breakup point? So we know that typically, suppose you consider a root locus with the poles somewhere here like this, and suppose the poles are like this. Now we know how does a root locus comes here. So this is where the root locus exists, and this is where the poles will go. And we know that there are three asymptotes. There is some transcentroid, and these are the angular asymptotes, and it breaks somewhere here and then goes like this. So this is the root locus, and we are looking for a breakaway point where between, assume that this is at -1 and -4 and this is at -10. We are looking at a breakup point between -1 and -4. So it will be of course more negative than -1, but it is less negative than -4. It lies between -1 and -4. Since we know that it lies between -1 -4, and we know that as the value of k is equal to 0, k is equal to 0, the closed loop poles are there at the open loop position. As the value of k increases, the closed loop poles started moving. Okay, one is moving towards the right here, this is moving towards the left. At some point of k, at some point of k, these two roots will meet. So at some, because this is k equals 0, k equals 0. So as k increases beyond 0, this starts moving. For a particular value of k, they will going to meet each other. So that value of k will be maximum on this part of the real axis. So you are looking for k max between s is equal to -1 and -4, where the roots will meet. So you are looking for that value of k which is maximum, so that roots are repeating, roots are overlapping here. So that's what is k max. So what is this k max? This k max is nothing but it is the value of k for which the closed loop poles are meeting each other, which corresponds to breakaway point. If the value of k is more than this k max, then poles will become complex. Poles will become complex. So how do we get to know this k max? This k max can be got to know from your del of s, because assume that, so let us just take an example. So del of s of this is something like s minus, sorry, s plus 1, this is s plus 4 plus of s, into s plus 10 plus of k. So you'll have some quadratic equation. So now you're looking for and the value of k, which happens to be some value of k, will get it. So then you do differentiate this k with respect to s. So whenever you're equating 0, we know that in mathematics whenever you have a value of any value which is maximum, if you differentiate that with respect to s, okay, this is dk by ds equal to 0 means you're trying to find the value of a at which system is having poles repeating. So that value of s will be corresponding to value of k which is maximum. That's why when you're equating this dk by ds equal to 0, you will get that value of s for which roots are repeating, and that will correspond to value of k which is k max. So that's why we do this dk by ds equal to 0 to find the breakaway point. Next comes, is it necessary to find the breakaway point to plot the root locus in all transfer function? It is not necessary. Assume that if you have a transfer function, gfs into hfs equals k by, now assume that it is s plus 1, this is s plus 3 and s. So in such case, you write the, this is this, and you have this, and you have this here. Now we know that this is where the root locus comes, and this is how it goes. Since there are no roots coming in opposite direction, there is no need of finding BAP. So you are not supposed to find any breakup point because roots are not coming in opposite direction at all. Suppose if we have GFS into HFS is equal to k into s plus 1, it is s square or s into s plus 3 and s plus 4. So let us see where the poles and zeros are. This is over here minus 3, this is minus 1, this is minus 4. Here you can see this is where the root locus exists. It goes here, goes here. So no BAP required. So there is no point in finding a value and then dk by ds, and then you're not supposed to find breakup point at all. When you need breakup point, assume that the same transfer function, assume that if it is gfs into hfs is equal to into s plus 1, s plus 4, assume that you have something like this. So s into suppose it is x square itself. Suppose it is x square itself. So what do you have? You have repeating poles here, and you have this here, you have this here. So this is minus 1 minus 4, this is 4. So one more important point is that whenever you have repeating poles, so repeating poles will will have will have will have breakaway point at, at their their own position, their own location. So where are the repeating poles? Is at 0, is at origin, so it breaks there itself. So one of the BAP is 0, and once it breaks, it has to come here. So they have to meet somewhere between 0 and minus 1 and minus 4. So you are supposed to find BAP or meeting point. We say it as meeting point where the poles will join together, and here you are looking for K minimum. K minimum. Whether it is K minimum or K maximum, you can get it using dk by ds equal to 0. Because for both the peak as well as for the valley, which is s here on y-axis or x-axis, k here, this is k max. This corresponds to BAP, and this is the value of s. So this is your k. This is k min. So this corresponds to meeting point. Meeting point. So it is not necessary to find breakpoint point in all cases. So this was our question number 13, and in 13 of course we had sub question which is what is the significance of DKBDS. Next have a look at does This 14% is centroid of asymptotes. Asymptotes will help know the stability of system. Now the question is, does centroid of asymptotes will help to know the stability of the system? So the answer is yes. Answer is yes. So take an example where GFS into HFS is K into S plus 1 is S into S plus 4. What is the centroid of this? Centroid of this is 0 minus of 4 minus of minus 1 by 1. Or let us take let me just take this. Okay, let me just take one more S plus 3. So this is another minus 3. So now where do you have this is that this is minus 6 by that minus 3. See now you have this here, this is here, this is here, this is here. If you look at them, so there is a centroid somewhere here, centroid somewhere here, and it will show that it actually goes there. Since you can see centroid is there on the left hand side, system is stable. System is stable. You just simply just see if I make this 10. The moment I make this 10, can you see this becomes 10? Can you see this now becomes this is plus 3 and this will become plus 1. Can you see this has now become the centroid has come to right hand side. So this will go here, they will take here, and system has become, the moment you made this, centroid is there at centroid is there at plus 1.5. The system is conditionally stable. If the centroid comes to the right hand side of this plane, then system is conditionally stable. So I can take another example where you have, so maybe we can take this, so GFS into HFS. So I can take, so you have K into S plus 1, it will be S minus 3 and S plus 4 and S plus 8. Now you can see the poles, there is a pole at 3, this is at the minus 4, this is at the minus 8, and this is at minus 1. You can see this actually comes here, pole actually here and somewhere it actually goes. System is now conditionally stable because centroid is there on the left hand side of the screen. So this will tell you system is conditionally stable. So yes, centroid of the asymptote will help to know the stability of the system. Next question is it necessary to draw the Rhodes array all the time? This is 15th question. Is it necessary to write a Rhodes array to plot root locus? It's not always true. No. Depending on the asymptotes number you can decide to write Rhodes array or not. assume that if asymptote is, just take an example, GFS into HFS is equal to 3 into S plus 1 is into S plus 6. Is it necessary to write the root survey? See here, you have this, you have this here, you have this here. So this is minus 1, minus 6. What are the root locus looks? It goes like this. You have only one asymptote. When you have only one asymptote, it is not at all crossing image axis, no need of root survey. A Routes array is not required. Routes array not applicable. Not applicable. Just consider the case where GFS into HFS is equal to K into S plus 10. Here it is S into S plus 3, S plus 6. Now see, you have one here, you have one here, you have one here, and you have minus 10. This is 3, this is 6, and this is 5. So where is centroid? If you see the centroid comes to the right hand side, because it is minus 3 minus 6 plus 10 by 2. So it's on to 0.5. So when it is 0.5, what happens? So this settles here. This is actually going in opposite direction. This is going in opposite direction. It actually goes like this. So you need to find, you need the right root survey. Routes array is required. It's required here because it is crossing the image axis. So array is required here because the asymptote is there. Suppose if the same thing, if this becomes minus 2, sorry, if this becomes plus 2, then routes array is not required. You can see here, the moment when this becomes to this side, you have this here, you have this here, this here, this here. This settles here, and this is actually going like this. The centroid comes somewhere on the left hand side. It just goes like this. It's not crossing image axis. Roads array not applicable. Here roads array is required. Roads array is required. Here it is required. Here it is not required. Here it is not required. So you decide. Suppose assume that if the number of asymptotes are 3. So assume that you have GFS into HFS is equal to K into S plus 1, S plus 4, S plus 5. Then naturally you have this here. You don't have centroid somewhere here. It actually goes like this. So this is where it is breaking. This goes this way and it has to cross. So the route surface is required. If it is 3 or more than 3, if it is 4 also, then actually we know that the this is going to cross the image axis. And actually when you have 4 asymptotes, 3 asymptotes, you are supposed to write the roots side. So just see whether the roots are going on to right hand side. Of course, so by this time we are sure that if the asymptote is there here and it is only 2, you are not writing. In this case, even though asymptotes are 2, you have to write the roots array because you know that. So it is crossing the match axis. Of course, a bit of prediction is required to decide whether roots array is required or not. Otherwise, it will be suppose if you try to find roots array for value of k for marginal stable system, you'll get some negative value of k. So you tend to panic. Hey, what is this negative value of this stuff? So that's where you should be a bit thinking, or you should be in a position to know where does a root locus exist, and then you can decide whether it is necessary to write the roots or not. If you have 3 or 4 asymptotes, then you are must to write the roots. So 16th question. What can be 16th question? Okay, let us move on to Bode plots or the frequency response, uh, especially Bode plots. Uh, in Bode plots, what type of transfer function is required required to plot the Bode. Of course, we need time constant form time constant form of open loop transfer function to draw the Bode plot. Why this? What is this time constant form? Assume that you have a transfer function gfs into hfs is equal to some 40 into s plus 4 and s into s plus 6 and s plus 10. Suppose you, okay, let me just take it as some 100 and this as 50. If you have something like this, take it as some number 400. So now, how do I? This is in pole zero form. So what I have to do is it is 40. Take out 400 outside from this. This will become 1 plus s by 400. This will become s into 50 outside. It is 1 plus s by 50. Take out 100 from this. 1 plus s by 100. So now this is, you have 40 into 400 divided by 50 into 100. 1 plus s by 400. It is 1 plus s by 50 and 1 plus s by 100. So you can, this will go with this will go with this, and it is now 16 by 5. So on. So this is now, this 40 was 40 was a root locus gain. Root locus gain of the system. 16 by 5 is system gain. Of course, if there is any, hope this is correct, system gain. So this is a difference. So I should bring this into time constant form, which will yield a system gain on the open loop transformation. Once it is this, so then you have to start the transfer function looping. Correct? Time constant form, from pole zero form, you should bring it to time constant form. If it is already in time constant form, then you can proceed. So what is the difference between time constant and pole zero form? A pole zero form will have it as s plus, okay, maybe assume that s plus z1, s plus z2, s plus p1 and s plus p2. This you can, the quotient of s is always 1. Whereas in time constant form, it is 1 plus s tau z1, 1 plus tau, okay, s into tau z2. This is 1 plus s tau p1. This is 1 plus s tau p2. So here you can see it's always 1 plus something, 1 plus s tau. This tau can be 1 also. This tau can be 1 also. But the thing is that you have to have 1 plus s tau, 1 plus s tau. So this is time constant form. Time constant form. This is Poisson form. Poisson form, it is s plus something. Whereas in case of a quadratic term, assume that you have something like s square plus 4s plus 49. This is the pole zero form. To write its time constant form, you have to take out this 49 outside, then this will become 1 by 49. This is s square by 7 whole square plus 4 by 49 into s plus 1. So this is time constant. This is time constant form of a quadratic term. This is the pole zero form. This is the pole zero form. Here the root locus gain is 1. Here the system gain is 1 over 49. This is the, you are simply taking 14 in outside. You are taking this omega n square outside. Because this is of standard n square plus 2 zeta omega ns plus omega n square. So this is the standard form. You take out omega n square. This is how it comes. This is time constant form. This is positive. Okay. Next, why time constant form is preferred for Bode plot. This is the question. So assume that you have a 10 time constant form. Assume that this is 100 1 plus s 0.1 1 plus s and 1 plus 0.02 s. So now when you're writing the magnitude part of this, what do you write? So what is the magnitude of this? This is 20 log 100, which is 40 dB. So this is 40 dB. How about this term? So this term is nothing but a term is going to have a magnitude of 0 dB till 10 radian per second. You can see this is till 10 radian per second it is 0 dB, and then it goes with a slope of plus 20 dB per decade. Plus 20 dB per decade because this is a 0. How about this? This is a line with 0 dB line till 1 radian per second. Afterwards it goes with a slope of minus 20. Here this is 1 radian, this is minus 20 dB per decade. How about this? This is again a 0 dB line till 50 because its cutoff frequency is 50. So till 50 it is 0 dB line and it goes with a slope of minus 20 per decade. So again minus 20 dB. The advantage of having them in time constant form is all of their contribution starts after their cutoff frequency. You can see what is the contribution of this till 10 dB per second, it is 0 dB. So then what is the magnitude of your system? The magnitude of the system is due to only this. So you can see till 10 here, till 1 radian per second, what the magnitude is only contributed by this 100. So after between 1 and 100, who is contributing? It is this term as well as this term. So it is, these two terms are contributing. And from 10 onwards, it is the contribution of this, this and this. So that's why if it is in time constant form, we can simply write all other terms contributions as 0 dB till its cutoff frequency. Suppose if it was not there in time constant form, assume that, so this comes out to be, so if I take out 0.1 outside, is it not 10 plus yes, and this is 100 into 0.1, and this is 1 plus s. Let me take out 0.02 outside. Is it not s plus 50? So now what is this? So this is how much will be this? Let me just do that. So it is 100 into 0.1 divided by 0.02. So this is 500. So 500 is what? Is my root locus gain. So it is now s plus 10. It is 1 plus s, and it is s plus 50. So what is s plus 10? S plus, okay, what is 10 log of 500? It is 20 log of 500 is this magnitude, which comes out to be 20 log of 500 is 54 dB. 54 dB. So this is this term. How about this term? This term is not 0 dB till 10 and then going down. So this will have some magnitude. And then it will come down. So how much the magnitude you need to find? How about this? This will certainly have a 0 and then sorry, this is going up because this is a 0. And how about this? This will have some magnitude and then goes down. Can you see each one of these terms have different magnitudes? When each one of them has different magnitude, what is the overall magnitude? You need to add all of them. You need to add all of them. Since you need to, of course, this will actually become, but this will be negative. This will be coming beneath. See now, each term in 40 form have got some magnitude till the cutoff frequency. So that becomes a problem while finding the overall magnitude of the system. Whereas if it is in time constant form, it is very easy to write the what magnitudes of each of the term, because its contribution is 0 dB till cutoff frequency, afterwards slope of so and so. This contribution is 0 dB till 15, then goes with minus 20. This contribution is 0 dB till 10, and then goes with plus 20. Okay, then it is very easy to add the plot here, because once you add the plot, the slope table will take care of the next part of the graph. So that's why it's very important to write the transfer function in time constant form to plot the Bode plots. Fine. So next is 18th question. What is the importance of omega? Importance of omega GC and omega BC. So let us see the importance of this omega GC and omega BCs. Of course, we know that in a system having, let me just continue in the next video.